All right, this last topic that's covered in Chapter 3 is going to focus on graphing quadratic inequalities. So we had touched on linear functions, absolute value functions in Chapter 0/Chapter 1 and 2 at the beginning of the year, but now we're going to be talking about graphing quadratics. So some of the rules still apply. So if it's not equal to, such as 1, this is a dashed line. And then in order to graph it, we're going to use some of our knowledge from the beginning of the chapter. So we're going to calculate the axis of symmetry, which is x equals negative b over 2a. It doesn't matter if there's an inequality. The b, the values are all going to still stay the same. So we have 3 over 2 times 1, which is 3/2. Our y-intercept is still the c value, which is 0, 2. And our vertex, we're then going to take the 3/2 that we got with our axis of symmetry, and we're going to sub that in so that we can get exactly where that point is going to lie on our graph. 9/2 plus 2. So if I get common denominators here without a calculator, I get 1/4. So then I get the point for the vertex as 3/2 negative 1/4. So you want to try to get as much of an accurate graph as possible. So we've got axis of symmetry is 3/2, so that's about 1.5. Or that is 1.5. We have a y-intercept of 0, 2. And then we have a vertex of 3 and then negative 1/4. And this one opens up because the x squared is positive. So I know it's dashed, so what I'm going to do is just sketch a dashed parabola. Oops, just like that. So now the last piece that we have to figure out is, okay, I need to be able to shade. Where am I shading this? So when you do this, what you're going to do is you're going to test values. Now, you have to just test anywhere on the graph itself. You don't want it to be on the parabola. You want to just test somewhere that is not on the parabola itself, but it could be any point to determine the truth value that's going to work out. So let's just say I pick the point 2, 4. So I'm going to pick 2, 4. That looks like it would fall within that parabola, or just not on the parabola. So I'm going to take that, and I'm now going to sub that into the equation. So here's my equation. So 4 is greater than 2 squared minus 3 times 2 plus 2. So 4 is greater than 4 minus 6 plus 2. 4 is greater than 4 minus 6 is negative 2. We get 0. So is 4 greater than 0? Yes, it is. So that is a true statement. So if that is true, wherever 2, 4 falls, that's true. And everywhere in that region is, which means I'm going to shade everywhere inside of that parabola. Now, if I got it so that the statement was false, I would then shade wherever 2, 4 was not, so that would be on the outskirts of that parabola. But again, testing the points is the crucial part. And you only need to test one, because if it's true for one, it's true for everything in that particular region. So not only are we graphing on a coordinate plane, but we're going to be graphing on a number line. So to graph quadratic inequalities on a number line, we're going to find the roots of the related quadratic equation by factoring, completing the square or the quadratic. And then the two roots, we're going to divide the number line into 3 intervals, and we're going to test. So in 2's case, step 1, I'm going to bring the 2 over. I also see this, so I know that I'm going to have closed circles on my number line. But the 2 has to come over. So I get x squared plus x minus 2. And I'm just going to temporarily set that equal to 0. So now I'm going to factor. So I'm looking for 2 values that multiply to get 1 and negative 2, which is negative 2, and add to get a positive 1. So that's 2 and negative 1. So if I set up my fractions, I find out that they do not simplify anymore. So I get x plus 2, x minus 1. And I get 2x values, negative 2 and positive 1. So those 2 values will now go on my number line. Negative 2, positive 1. Keep in mind, you know you have negative infinity and positive infinity. There, it's a closed, it's equal to from the start, so I know I'm going to have closed circles. So to determine where my arrows go, I've now broken this up into 3 regions. Region 1, Region 2, and Region 3. And what I'm going to do is I'm going to test my values in each of those regions. So I'm going to pick -3 in Region 1. I'm going to pick 0 in Region 2. And then I'm going to pick 2 in Region 3. And I'm going to type those in. So my inequality is right here. Notice there's only an x. So I have -3 squared plus -3 is less than or equal to 2. 0 squared plus 0 is less than or equal to 2. Or 2 squared plus 2 is less than or equal to 2. And I'm going to simplify. So I get 9 minus 3 is less than 2. So 6 is less than or equal to 2. 0 is less than or equal to 2. Or 6 is less than or equal to 2. And I'm going to look and say, okay, well, this is false. This is true. And this is false. Well, if the middle one is the one that's true, that means that when I draw my arrows, they have to be coming together like this. So this is the region that I want because that, again, matches up with my true statement that I have over here. Now, the other piece that we're going to continue with from the beginning of the year is our set builder and interval notation. So let's see if we remember that. So set builder has those little squiggle brackets. So this is for all x, and according to this, they come together. So this is a compound inequality. So that means we have, for all x such that -2 is less than or equal to x, which is less than or equal to 1. In terms of interval notation, we only have one branch here, which means I only need to have one interval, and it's -2 to 1. And they're both closed circles, which means they both will get brackets on them. Okay, but the whole goal, and just keep in mind the testing is crucial. All right, second one here. So everything's on the right side. Again, we have closed circles. And we get lucky again in terms of, can we factor this? So let's see. AC is 1 and 30, which makes 30. B is 11, so yes, we have 5 and 6. When I make my fractions, I don't have to simplify, so we get x plus 5, x plus 6 equals 0, and we get -5 and -6, which are our two values on our number line. Just make sure you put them in the right spot. We have -infinity and positive infinity. And they're both going to be closed circles again. Okay, so we have 3 regions again. 1, 2, and 3. And we're going to test. We're going to test values. Here's our problem. X squared 11x plus 30 is greater than or equal to 0. So for region 1, I'm going to take -7. For region 2, unfortunately, you're stuck with a decimal. And for region 3, I'm going to go with the easiest, which is 0. And you're going to plug each one into the equation. You have plenty of room, so if you got to go to the bottom, definitely do that. So 0 plus 0 plus 30. All right, when you simplify everything out, you should get 2 is greater than or equal to 0, -0.25 is greater than or equal to 0, and 30 is greater than or equal to 0. So we find here that we have a true statement, false statement, and a true statement. So in this case, our trues are the bookends, basically. So our arrows should be going to the left and the right when we graph these, because the middle section doesn't apply. These are your trues. So in terms of set builder now and interval notation, because there's 2 different branches, this is like an OR situation. So for all x such that x is less than or equal to -6, or x is greater than or equal to -5. And for interval, we have 2 different intervals. So one of them is composed of -infinity and -6. The other one is composed of -5 and